No, I don't think so today.
Oh, yeah,
E night, yeah, it's great. All right. I don't write them all. Like, I find some of them positive. All right, so, all right, so here's the first of a few.
This is 5-4, right?
It is 5-4, so we're back in chapter 5. This talks about the definite integral of k times f of x. And if you actually go back to pre-calc, where k is some constant, what does multiplying f of x by a constant do? Stretches it which way? Vertically. So what's that going to do to all the rectangles when you add them? It's going to make them taller. How many times taller? Okay. So if you have a constant times a function, you can actually take the definite integral of f of x and multiply it by k. So constants can come back and forth in front of and after the definite integral sign. Constants are fine moving back and forth. And why? Because constants are just multiplying the area, and it doesn't matter if you multiply the area after you find the area or if you multiply the function to find taller rectangles to find the area. Is that intuitively okay? As a matter of fact, I have a question for you. What if I asked you this question? Let's think about it in terms of a picture. It's a straight line, and it's a by b, and I want the definite integral. So that's going to be a box, which the width is, some people are saying, b minus a, and the height, k. That's good, all right? Hey, we didn't even need our calculators. All we need to think about is what the picture is going to look like, and then we use some geometry. All right. I don't know if that's a property but it's an interesting thing that we talked about. So, all right. Let's see. Here's something that we talked about briefly. So the definite integral from a to b of f of x dx is the opposite of the definite integral of b to a of f of x dx. So integrating left to right gives you the opposite of integrating right to left. And I think we did talk a little bit about that. Is that true? Dan says yes. Anyone else say yes? Maybe? Yeah, okay, fine. And just, you're more than welcome to write these properties down. I'm totally fine with that. Just to let you know, I think they're all in blue boxes in the book. So I'm not today's not one of the days that I'm doing anything that's not already somewhere else. All right. Whoops. If I have the definite integral from a to b, and I add to it the definite integral from b to c, okay? If we think about it in terms of a picture, that's what I think we're going to try to show you. If we take the area, we take the area here and the area here, we can say that quite simply as just find the area, David, what'd you say, from A to C. So, in many respects, the definite integral behaves as area. You can add up two areas to get the area of the whole thing. Alternatively, if you have the definite integral from A to C, you can break it up into two parts, if you'd prefer. Okay, you can break it up into parts, and that's okay as well. And then, if you have, this one's a little bit harder to visualize, but if you have two different functions, and you want to find the sum of their areas, you could actually just add the functions and take the definite integral of that whole thing. And I'll try to draw a picture for that. Maybe I'll use blue for f of x, and I'll use red for g of x. So the definite integral of f of x is the blue, right? I don't know why I used thick, sorry. And the definite integral for g of x is the red. That actually would be the same exact thing. Oh gosh, I have another good thing to tell you, but alright. There's so many things I could tell you about definite integrals. That'd be the same thing as if I added the function. So if I added g of x and I added, that's not g of x, that's supposed to be f of x, sorry. If I added f of x and I added g of x, can you see the height of that rectangle, of those two rectangles added up would just give me a really tall height? So I don't know what it would look like. Maybe that's what the whole thing would look like. Would it just be a much taller area, adding those functions? That was a little confusing, wasn't it? So yeah, sorry, I apologize. That was not that good. If I have the sum of two functions, I can break those down into the definite integral of one of the functions plus the definite integral of the other function. So, for example, if I have, let's say, the definite integral from 0 to 1 of x squared plus x, that's the same as the definite integral from 0 to 1 of x squared plus the definite integral of x. Okay, and maybe we can actually look at a picture of that. Will that help, maybe? Okay. So this is not a proof, but it is trying an attempt to do a convincing argument. So let's do, we have x squared, and we have x, and we'll put that on the big screen, and we will do window from 0 to 2 will be plenty. And I think we can do 0, whoops, that didn't work. Let's try that again. Alright, so we're looking at from 0 to 1. So I could either do second Calc 7 x squared. Actually, we know what that is, I think. Didn't we do that yesterday? Isn't it like 2 and oh, it's a third. Sorry, we did from 1 to 2. Alright, so a third. Sam, remember a third. You got it? Mm-hmm. Alright. Stop it. If I do Calc 7, this time, see it's still on x squared. If I use the arrow, I can arrow down to y equals x. And now if I find the area from 0 to 1, it's 0.5. Alright? So the area, the definite integral of x, Drew, remember half. Sam, what are you remembering? 1/3. 1/3. Alright, so let's go back, and instead of doing either one of these functions, let's do the function x squared. Actually, I wonder if I can do it on top of it. Hold on. X squared plus x. And I think I will clear that out. Alright, so there's x squared, here's x, and here's the sum of those functions. If I add these two functions, you should see this height plus this height gives me this height. Every time you look, when we add those, as a matter of fact, at 1, what's x squared plus x when I plug 1 in? 2. 1 plus 1, right, is 2. So let's do it. Let's do Calc 7, and let's go from 0 to 1. We're hoping that we're going to get, oh, bummer. Second Calc 7, arrow down, 0 to 1. 0.833, that's some crazy number. What's that? 5/6? Hey, what's a half plus a third? It's 5/6. Okay? So not a proof, but an argument that this is the case. Sorry. I was doing well there. I was just sort of cruising along and then I got a little convoluted. My apologies. Let's take a look. Some classwork. Let's see what can be easy and what can be... sometime... Remind me to go back to 12 at some point. It's not going to be today, but we should do 12. All right, 16. All right, Dan. We have some given information here. Yeah, we know from 0 to 5, the definite integral is 10. From 5 to 7, the definite integral is 3.
Okay, so for A, it would be 13.
Great. Calling someone for B.
Alicia.
10.
Close. What's the difference here? What? So, look at the... That's what I'm looking for. Say it again, loud and proud. Yeah. Okay. So the difference between 0 to 5 and 5 to 0 is one's going left to right, the other's going right to left. Okay? Alicia, calling someone for C.
Is that 0?
It is. Right? How wide is that? 0. I don't care how tall it is if its width is 0. Morgan, D. It definitely would. How'd you get it? You got it. All right. That wasn't bad, was it? Okay, let's keep going. 17. Morgan, call on someone. Now, this might be a little harder. You might have to... No. Very close. Yes. Let's think about that. From negative 1 to 1 is 0. That means all the area cancels out from negative 1 to 1. And from 0 to 1, the area is 5. So what must have the area been from negative 1 to 0 to cancel it out? Negative 5. Okay, a little bit harder, right? All right, David calling someone for B.
0.
You got it. 2 times 0, that's fine. I just made everything twice as big, but I still have twice as much negative area and twice as much positive area. They're going to cancel each other out. Calling someone, Drew. I think so. People feel all right with that? All right. Rachel calling someone for D.
10.
All right, I got to think about this. All right, from 0 to 1 is 5, and we're going to minus negative 5. All right. How do people feel about that? 10? All right, good. So the area from 0 to 1, or the signed area from 0 to 1 is 5. We were given that. And then based on someone's argument. Whose argument? David's argument, negative 5. So 5 minus negative 5 is 10. Is that okay? All right. Let's keep going. Oh, 18A is my absolute favorite. You're going to get it wrong. All right. Okay. Someone give me the wrong answer. Actually, let's do B first. Let's do B. All right, you want to do A first? All right. All right, so for A, I need the wrong answer for A. All right, Dan, what's the wrong answer? 6 is totally wrong. It couldn't be more wrong. There are 2 ways of thinking. Oh, do you want to give me the right answer?
No, I was just going to ask something.
Go ahead.
Wouldn't it be like 0 gets 0?
Can you not have an answer? Because it's not...
No, we totally can have an answer.
Oh, I think that I can do this.
All right.
Well, I'm just going to wait. No, that would only work if it was boxed.
Because you don't know if it's continuous after x equals 5, so how can you...
What does the plus 2 do to the function? It raises it up. So I want you to think about that. If you have a function f of x from, 0 to 5? Sorry, I don't know what. And we raise it up 2 units. I think it is 14. You want to give me at least one convincing argument, and then maybe we can...
Well, so you're adding functions, so if f of x equals 2, it's going to be 2 all the way across. 2 and like...
So you see the second function, you think y equals 2.
Yeah.
So from 0 to 5. So you're thinking about, hey, this is really f of x dx plus 0 to 5, 2 dx.
Right, yeah.
I can break it up into two different functions. I know what this is, right? This is 4. What's this? What's this a picture of?
2 by 5.
A 2 by 5 box, right? And that would be 10. So if you think about it like graphically, that's what f of x does. What does f of x plus 2 do? Well, you already told me. It lifts it up 2 units. So can you see that all we're really doing is we're taking that same area, but we're putting it like on a pedestal? Pedestal, right? We're putting it on a pedestal. And how big is that pedestal? Well, it's 5 wide and how tall? 2, right? So that box is exactly what we're putting the function on top of. So you can think about it as Drew did algebraically, or you can think about it as a picture, graphically. I love that question. That's a great question. That's a nice answer, too. All right, let's try to do B. Is B easy or hard? What does the 2 do in this case?
It's like horizontal shift.
Horizontal shift.
So it's
Oh, so
4.
It's 4, right? All we're doing is shifting the function back. And what do we do with the limits of integration? We shifted those back. Right? All right. Hey. Yeah?
Even means it's across the x-axis, y-axis is symmetric.
Yep.
Okay. And odd is across the origin.
Yep. Have a terrific Tuesday.
Tremendous.
No.
Tremendous Tuesday. I like that. Have a tremendous Tuesday.
Give Quibble
Terrible Tuesday.
No.